velocity as well as the angular velocity. So what we know is that the linear velocity and angular velocity are given by this formula: jv1, jv2, jv3, j omega 1, j omega 2, j omega 3 times theta 1 dot d1, sorry, d2 dot d3 dot. So how do you find the j's? Well, how many j's are there? Well, what you do is you always write the degree of freedom. This is 3 by 1. This vector v is, there are three velocities: x, vx, vy, vz, and omega x, omega y, omega z. So this is 6 cross 1. Okay, and so this will be times 3, 6 times 3, right, for this to be consistent. So in the last class, I derived a formula for the Jacobian. Okay, I'm going to rewrite that, and then we'll go from there. Okay, so let's do this recall. That jvi equals ri minus 1 ok cross and ri minus 1 ok. This is, the first formula is for the revolute joint, and the second one is for a prismatic joint. Okay, so depending on the joint, you would choose the appropriate JV. Similarly, for J omega, we have Ri minus 1 with respect to O, K, and 0. The first one is for revolute, the second is for prismatic. Hey, when I say 0, it really means it's a matrix, it's a vector, 1, 3. Okay, so you write 3 zeros in a row format. Okay, so let's use this information here to write the different j's, and after we write the j's, which is probably the hardest step, the other part is evaluating these variables, which is probably the easier one. So let's write the jv's here. Okay, let's start with jv1. So I put I equals 1. The first joint is revolute. Like you can see, this is a revolute joint, so corresponds to theta 1 dot. So I need to look at the formula for the revolute joint. Okay, On is the end effector. I is going to be 1, first link. So what I would have over there is R 0 with respect to frame 0k crossed with On, which is basically the end effector. So the end effector is at O3. You could write P if you want, but really that's the origin of the third frame. So I'll write this as O3 with respect to 0 minus O, I equals 1, so O is 0, 0. So that's my first Jacobian. Okay, the next one is JV2, corresponds to D2, which is a prismatic joint. So the next one is prismatic. I use this one. So I put I equals 2, so I get R1 with respect to 0. Okay. Okay, and then finally JV3, that's a prismatic joint. So prismatic joint formula is this. I put I equals 3, so R2 with respect to 0. This is theta 1 dot D1 D2 dot D3 dot. Let's see if I can get some space here. Okay, so I'm done with all the JVs. Let me go to J omegas. So J omega 1, so I need to choose one of the two. In this case, the first one corresponds to a revolute joint. So I choose the revolute joint formula, put I equals 1. So I get R R00K. That's my first one. The second one is J omega 2. That corresponds to a prismatic joint D2. But the formula for prismatic joint is simply 0. So I'll put a 0 and then 0. This will make it better, clearer. Okay, what remains now is to find the R's and the O's, and I'm done. So let's find the R's, R10, R20, R00. And to do that, we need to find A10, A00, and A20. They come from the DH formula, which we've seen before. Okay, so let's write A00. Now A00, any vector with respect to frame, so I with respect to I is always going to be the identity matrix, which is 1 0 0 0 0 0. Okay, ones on all the diagonals. A10, this one comes from the formula for the DH, and you can do it by hand, or I would recommend using MATLAB, the symbolic toolbox. This is cosine 1 sine 1 0 0 minus S1 C1 0 0 0 0 1 0 0 0 D1 0, and then A21, okay, and then A32 is simply that's the identity matrix for R23, and then 0 0 D30. Sorry, this should always be 1. Okay, now I'm all set to find the individual values. So I find A20 first. A20 is A10, A21. By the way, C1 is cosine theta 1, S1 is sine theta 1. So A20 is, you got to first take A10, which I wrote down, A21 which I wrote down, and then multiply the two, which is clearly something you can do by hand, but I highly recommend using MATLAB. This comes out to be C1 S1 0 0 0 0 minus 1 0 minus S1 C1 0 0, then 0 0 D1 plus D2 1, and then yeah, this one, yeah, this one. A30 is A20 times A32. Again, do the multiplication to get C1 S1 0 0 0 0 minus 1 0 minus S1 C1 0 0 minus D3 S1 D3 C1 D1 plus D2 and 1. Okay, I think we are all set. What we are after is, if you go back, we are trying to evaluate R00K, R10K, R20K, and then of course these two things. Okay, so let's try to write them down from the formula here. So O00 is simply 0 0 0, right? Because that's the origin. So done with that. O30 is actually this part, O30. This gives you the position of the end effector P, right? So O30 is done. This, by the way, is R00. This thing here, this matrix is R10. This matrix is R20. Okay, so if you want to find what are we after? We are after R00 times K and R10K and R20K. That is simply the third column of R00. So I'll write that down. So R00K is simply the third column, this one. That will be 0 0 1. And then R10K is the third column of this, of R10. So that's again 0 0 1. And then R20 is again the third column, which is this, minus S1 C1 0. So this is K. Okay, so everything over in the equation here is known, right? Everything O3, O0, everything is known. All you got to do is now is to do this cross product. The other ones are pretty obvious. This one is probably the hardest one. You can use the cross in MATLAB, or you can use the skew symmetric part. Yeah. So this is known. This is known, right? It is over here. That's O30. Yeah. Sometimes people, well, let me write this as 0 0 0, so it's consistent with O30. It's a 3 row 1 column. Okay, so subbing in equation 1, we get Vp omega p, and so this is going to be, after simplifying, the formula is minus d3 minus d3 c1 minus d3 s1 0 0 0 1 0 0 1 0 0 1 sorry 0 0 0. Is that right? J omega 2. Yeah, it's 0 0 0. 0 0 1 theta 1 dot t2 dot t3 dot, and so these are the individual quantities we found out. So JV1, JV2, JV3, J omega 1, J omega 2, J omega 3. So now you can find the velocity of P if you know theta 1 dot, d2 dot, and d3 dot. So as I said, that's one of the main uses of Jacobian. You can find the velocities of any point. In fact, the previous problem I did, I only showed you how to find the Jacobian. You could find the Jacobian of, well, you could find the velocity of, let's say, this point, whatever you want. What you have to do essentially is the correct. So V omega would be replaced with V of O1, 0, V omega O1, 0. Then you write the Jacobians from that table, and then that will remain the same. This might be a little bit more trickier. If you look at my double link planar manipulator problem, which I did before this one, that has some tricky aspect to it. You might want to see that. There's, I think, a problem related to, yeah, so here in this particular case I also did Jacobian of point C. What is point C? Point C is this point. Okay, it's not the end effector. So how do you do that? You might want to go through this problem. I believe there's a question in the homework which talks about finding Jacobian of point which is not the end effector. Okay, so that's one use of the Jacobian. There's another use, and this is to do with static forces. So let me motivate this with an example, and you might have seen this in a first course in statics. Okay, so the problem is given this two-link manipulator. Okay, and this manipulator is in the horizontal plane, so it's not this way, but it is in this plane, and so gravity has no role to play. It's acted upon by force Fx, Fy, Fx acting in the x direction, Fy in the y direction at the end effector, so that's yanking onto the manipulator. We got to find the torques T1 and T2 at the two motors which are at the hinge joint such that this manipulator is in static equilibrium. It cannot move. Okay, so find torque 1 and torque 2. So this is a classical statics problem. The way you'll do it is you'll draw free body diagram. So this is method 1, which is drawing free body diagram. So how will you do it? You draw free body diagram for the complete manipulator FBD1. T1 will act here, Fx, Fy, and this angle is theta 1, and since that angle is theta 2, the angle made by second link with the horizontal is going to be the sum theta 1 plus theta 2, and then you'll draw another free body diagram, which is the second free body diagram only for link 2, that has a force T2 and Fx, Fy, and this angle is theta 1 plus theta 2, This length is L1, L2, L2, and writing the equations, it's basically you do of what is known as take moments about point O, and this is O10. Take moments about the origin, right? And so the torque T1 should be equal to torque 1, my bad, torque 1 is counterclockwise, so you assume this, our assumption is counterclockwise positive, clockwise negative. Torque 1 is counterclockwise, so it's positive. Fx acts that way, and about point O it's going to induce a clockwise torque, so the sign is negative. Fx times the distance from this point all the way to this line, right? So the vertical distance, this distance is L1 C1, L1 C1, and this distance is L1 L2 C1 2. So plus L2 C1 2. Okay, that's the torque due to Fx. Fy also induces a torque about point O0. Fy is inducing a counterclockwise torque, so it's going to have a positive sign. And the moment arm is the distance from Fy to O, so this distance. That distance is going to be L1 S1 plus L2 S12. So we have L1 S1 plus L2 S12, where C1 is cosine theta 1, S1 is sine theta 1, C12 is cosine theta 1 plus theta 2, S12 is sine theta 1 plus theta 2. So that gives me the value for torque 1, that is all equal to 0. So find torque, I just move things around and I have T1. If I want to find T2, which is by equation 2, I'll take moments about O10. So T2 is counterclockwise, so positive sign. Fx is acting, is going to induce a clockwise torque. You think of how will this manipulator move? Fx is only acting, it's going to be clockwise. So Fx times L2 S12, because this distance is L2 S12 with a negative sign, and Fy is acting counterclockwise, so Fy times L2 C12, because C12 is L2 C12 is this distance C12. So that is equal to 0, and I can solve for this one, solve for T1 and T2, right? That's how you would do it if you refresh your mind about how you did it in statics. Draw a free body diagram, take moment balance, and get the answers to torque. Now, turns out that using Jacobians, you can do the same thing without drawing free body diagrams. Okay, so I'm going to show you how to do the same calculation without drawing free body diagrams. There is a way in which the Jacobian gives you T2 and T1 without having to do all these things. So there's no trig involved. Okay. For torque. Using Jacobians. So when we wrote the formula for V and omega, remember we wrote that is equals J times q1 dot q2 dot so on, right? We wrote this down earlier. We derived this formula. What I'm going to do is I'm going to write this as x dot equals j times q dot. Okay, x is the way in which I can package v and omega together. But what is x dot? It is dx dt equals j times dq dt. I could also write this as delta x equals j times delta q. Essentially, I've got rid of the dt. So a small change in x, well, small change in q. What is a small change in q? It's basically small change in the motion of the joints, which is stored in delta q, will lead to some change in the motion of the end effector, right, which is x, and that is related through j. That's what it tells, this formula tells. Okay, now we're going to try to take this and try to relate it with force and torque. Okay, so if F is the force at delta x and T is the torque at delta q, so these torques are acting at the joints. Now I've been very specific here, but T could also be a force as long as this force acts at dq. So for a prismatic joint, it will be a force. For a rotary joint, it will be a torque. Then what I can do is I can write delta W is the net work done is F transpose delta x. So what's the definition of work done? Work done is force times displacement. So assume that delta Q turns by a small amount. Okay, that will cause x to move by a small amount. And because of the force F acting at delta x, the work done is going to be that. But there's also work going to be done at the joint. So torque transpose times delta Q. But when I'm doing this computation, this is a fictitious displacement. It's not a real displacement. This is called the principle of virtual work. Okay, essentially this displacements are fictitious. They are not real. What this is saying is that work done by this force at the end effector and the work done by the torques at the joints should all be equal to 0, because no real work is done, it's virtual work. So what I have is, from this formula, I can write F transpose delta x equals torque transpose delta q, but we call this 1 and 2. So I can do is put 1 in 2. So our F transpose delta x equals F transpose delta x is J transpose delta q from 1 here equals torque transpose delta q. But delta q is not equal to 0, so F transpose J equals torque transpose. Now what I'll do is take transpose of both sides. So when I take the transpose of AB, so AB transpose is always B transpose A transpose. So I get so this will be F transpose J, the whole transpose equals torque transpose transpose. So this will give me J transpose F equals torque, because AB transpose is, the rule is if you want to do AB transpose, it's always B transpose A transpose, something you probably did in your homework 1, right? Sure, this is true. And then transpose of transpose is the matrix itself. So this is the formula which relates torques with the forces through the Jacobian. So if you want to find the torque, which we did in the previous problem, you simply take the Jacobian, take its transpose, multiply by F. You're done. You don't need to draw a free body diagram. Okay. You do not need to know the derivation, just the application of the formula. Okay, so we'll take this formula and resolve the problem we did earlier. It's right here. Same problem. Two link manipulators is shown. Forces Fx, Fy also shown. Find torques T1 and T2 to keep the manipulator in static equilibrium. And as said, the manipulator is in horizontal plane, so gravity has no role to play. But I think your homework, I've rotated this, so it will be in the gravitational field. So you'll have to also put the effect of gravity. So what I'm after is this. So this is my method 2 for solving the same problem. It should give me the same answer as before using Jacobian. Okay, so the formula is the torque is the Jacobian transpose times F. So in this case, let's call this P. So force acting at P. Now, if I had put another force over here, say, then you'll have to plus Jacobian of that point times force at that point. So when you have gravity, gravity will show up here and here. You'll have to consider the effect of 2 points. So you'll have Jacobian of this point, center of mass, times mg crossed with mg, times mg in its vector form, and then Jacobian of that point, center of mass. So it will be 2 terms. Okay. So in this case, just 1 term because only one force is acting at P. Okay, so find the Jacobian of P. Fp is simply the forces Fx, Fy, 0. So those are the forces, linear forces. But really, what you want to put here is all the 6 forces. There are 3 forces coming due to linear forces. There are 3 will come due to torques. There are no torques at P, so you can put 0, 0, 0. So this is linear forces, which I've shown there, and these are, sorry, they're just the forces in X, Y, Z, and these are torques at P in X, Y, Z, which are clearly not there. That's simply 0. So then I need to find the Jacobian of point P, which is the end effector. So we've done, we can do it again if you want. Jacobian of this one of the end effector would be JV1, JV2, J omega 1, J omega 2. Since it's both are revolute joints, you go back to the formula, which is right here, right? So we're trying to find JV1, J omega 1. We are only looking at revolute joints, so we are looking at this one and this one. So the first row would have this formula because that's a revolute formula, and the second row would have J omega 1 for the revolute, so it will be that formula. So I'm going to write that down next. So R00K crossed with position of P. This is also O20, so O20 minus O0. Another one is R10K crossed with O20 minus O10. And then for the J omega, it's R00K, R10K. Okay, so this is something we have done in the past. I'm just going to put it down so you can refer to the. Let me put it down there first. L1. Let's check this. So if you go back to lecture, the previous lecture, then it's right here. This is the formula which I derived for the Jacobian of point P. You can refer to my notes there about how to find this. But that's the formula I need to copy paste. So L1 minus, sorry, L1 S1 minus L2 S12 L1 C1 plus L2 C12 minus L2 S12 L2 C12 0 0 0 1 0 0 0 1. So these three terms come from JV, these three terms from J omega. Okay, and so the last step is torque equals J transpose F. So there are two torques, torque 1, torque 2 equals J transpose. So that matrix, which is 6 cross 2, you're going to take that and take the transpose of it. So it'll be 2 cross 6. L1 S1 minus L2 S12 minus L2 S12 L1 C1 plus L2 C12 minus plus L2 S12, sorry, be C12, then 0 0 0 0 1 0 0 0 0 1, and then forces it's Fx Fy 0 0 0 1, sorry, 0 0 0. Okay, after doing the multiplication, so the 6 cross 2, sorry, 2 cross 6, 6 cross 1, so they're compatible. For multiplication, you get torque 1, torque for 1, 2 by, see, 1, 2, 3, 4, 5, 6, 7. Yes, I put an extra one. Yeah, this is better. So equals fx minus L1 S1 minus L2 S12 fx minus L2 S12 plus Fy L1 C1 plus L2 C12 plus Fy L2 C12. Yeah, if you like, just move this sign out. So I'm going to write it in a way you can compare. Okay, so that's the answer. So you can see it's, let's just check one of them. Minus fx L2 S12 plus Fy L2 C12. I think this might have been switched in sign. Let's see. This is the problem we solved. So let's check this one. Okay, torque 2 equals fx L2 S12 minus Fy L2 C12. I think there's a switch in the sign. There's a switch in the sign. Minus, the answer is the same, but there's a switch in the sign. What does that happen? So I don't doubt my free part. That looks right to me. See. So torque 1. Yeah, there's nothing wrong here. This it's positive, that's negative, that's right, that's positive. Well, that's also right. Uh, yeah, it's let me check this, but one of them is giving me so this one is giving the actual torque I need at the motors of the joints to keep this in place, but looks like what this one is giving me is not that torque. It's giving me the opposite. It's giving me the uh, what is known, there's a reaction torque, and there is a the there's a motor torque and there is a reaction torque, which is different. It's basically switched by signs. Let me check this. The answer is right. It's just switched on signs. That'll be true for also for this one. Let me clarify this. Okay, but the signs. Let me clarify that. Finish up this part with what is known as singularity, and you got to know this because this is something which comes up very often when people talk about manipulators. Is the manipulator singular or not? Okay, so what we've done so far is given, let me write it down, V and omega equals J times Q dot, right? So given the velocity, given Q dot, we can find V and omega. So given the motion of the joints, we can find the velocity of the end effector, which is one problem. The other problem is we need to find Q dot given the velocity of the end effector. So this is given, find Q dot. So this is given the velocity of the end effector, find the rates. That's the inverse problem, right? So sometimes you want the manipulator to reach this particular table at certain speed. You want to find how the joints move, how fast they should move, and that formula will help you do that. The issue is that here is what if inverse, so this inverse does not exist. Or what if this inverse is 0, or what is known as singular. So what if, better way to write it is determinant of JV J omega is equal to 0. So we know that the inverse is equal to 1 over the determinant times the cofactors of JV J omega. So if the determinant is equal to 0, then the inverse is going to be infinity. the inverse is going to be infinity, which means that q dot will be equal to infinity. So, which means that you're going to tell the manipulator joints to move infinitely very fast, and clearly no physical device can move infinitely fast. So this is an issue. So I think the best way for me to illustrate when a manipulator goes singular, so it's very important to know when the manipulator goes singular. So turns out there are specific orientations of the manipulator which will drive them in singular. And I'm going to show you what that singularity is for a simple two-link manipulator case. Okay, let's do that sort of, you'll be able to conceptualize what it really means to be singular from that example. So let's do a two-link manipulator and see when it becomes singular, that is the Jacobians become singular. Example of singularity. So this is the same two-link manipulator which we've done so many times. L1, L2, theta 1, theta 2. And for this one, we found that the velocity of point P the Jacobian for this would be 6 elements and so on, but in this case we're only interested in the linear velocity, so velocity in the x and y. So we have to truncate that 6 by 2 matrix and only find the first two elements. So Vx and Vy, and we call this, a better way would be velocity of P in the x direction, velocity of P in the y direction is, and this is from the Jacobian calculation, is minus L1 S1 minus L2 S12 L1 C1 plus L2 C12 L2 S12 L2 C12 times theta 1 dot theta 2 dot. So what we're trying to do is find theta 1 dot theta 2 dot by inverting the matrix here. Inverse, the inverse is C12 divided by S2. Okay, actually I'm going to simplify my life a little bit. Let's put, the calculations become very lengthy, so I'm going to put L1 equals L2 equals 1, and then take the inverse of the Jacobian J, which is this. So when I do that, I get theta 1 dot theta 2 dot equals C12 divided by S2 minus C12 I got to write this down full form because apparently you get half angles. Theta 1 plus theta 2 cosine minus cosine theta 1 plus theta 2 divided by 2 divided by sine theta 2 divided by sine theta 2 by 2, and the other term is sine theta 1 plus theta 2 divided by sine theta 2 minus sine theta 1 plus theta 2 divided by 2 by sine theta 2 divided by 2, and then here there would be VPX VPY. So that's the exact terms are not important, but what is important is that this term here goes to become singular, becomes singular when theta 2 equals 0, right? See, theta 2 is here appearing in the denominator, so when that equals 0, you'll see that the determinant becomes, so J inverse goes to infinity. Okay, so what is theta 2 equals 0? Let's let's draw the manipulator with this configuration. Theta 2 equals 0. We have the manipulator like this. Theta 2 equals 0. What we're trying to do is we're trying to L1, L2. So the manipulator is fully stretched position. What the Jacobian is doing is it's finding theta 1 and theta 2 dot given VPX, VPY. So given these quantities, put P and P. We're given this, we want to find theta 1 dot theta 2 dot. When this becomes infinity, what really is going on is you cannot move the manipulator in the x direction no matter what you do, because if you are in this stretched position, we will only move in the y direction. You cannot move in the x direction because you're fully stretched. So when you're trying to find theta 1, theta 2 dot, you cannot achieve a particular VPX because of the way this manipulator is set up right now. So that is the singularity. It basically is telling you to do what you cannot do. So let me put that down and I'm done. Here the manipulator cannot move in the VPX direction, but can only move in the VPY direction. Okay, and this is the singular position because one cannot find theta 1 and theta 2 dot to achieve a particular VPX. So it tries to set up infinite speeds. So when you're trying to control robots, especially in velocity, you never hit this critical condition. If you hit it, then it's all going to go crazy. And so people always talk about singular free configurations. Okay, so that's about